This conference will now be recorded.
All right, this is section 3.2 in Math 211. We're looking at one of the examples we did not get to do on the mean value theorem. So this is example 4 from our notes. And it said, let f of x equal 2 minus the absolute value of 2x minus 1. Show that there is no value of c such that f of 3 minus f of 0 equals f prime of c times 3 minus 0. Why does this not contradict the mean value theorem? So obviously the interval that they are trying to do the mean value theorem over is 0 to 3. And remember, the assumption here is that this is going to fail because it doesn't meet one of the conditions. And if you don't check those up front, then you don't know that it's not going to fail until you, because sometimes students will just plow through and say, I'm going to work it out. But then the conditions, don't meet it. So then it doesn't really contradict the theorem because it was never even set up correctly. So that's kind of the whole point of these types of examples, is just to make you aware that if you try to use a theorem when the conditions aren't there, you're going to be using something that may not give you anything that is true. So our function is going to be split up into two pieces, just like anytime we have absolute value. One case is going to be 2 minus the actual inside of the absolute value, and that happens when the inside is greater than or equal to 0. So remember, anytime your inside of your absolute value is equal to 0 or bigger than 0, you pretty much just get the value that you already have inside. So this minus right here does not mean we change signs or anything. It means we're just keeping the function as it is. The other scenario is where you're going to have a minus for the subtraction sign, but then the part that you get is going to be the opposite of the inside of the absolute value. In other words, your absolute value was negative inside, and you have to change the sign when you take the absolute value. So that happens when the absolute value part was negative inside. Now we want to clean that up a little bit. So this is going to be 2 plus 1, so that'd be 3 minus 2x for the top guy. And be careful here, this is really a plus, so it's going to be a negative 1, so that'd be 1 minus, or actually plus 2x, so 1 plus 2x. So those are my two equations. And then we'll want to solve these for x as well. So this one is when x is greater than or equal to 1/2, and this is when x is less than 1/2. That just clarifies the function a little bit more, instead of having all of these disjointed pieces that we don't really know, what the values are exactly. So this is what we graph if the x's are greater than or half or equal to a half, and this is what we would graph if they were less than a half. Now, for the actual mean value theorem, you need the derivative of this. So we're going to do f prime of x, or c, if you want to call it that. And we have to take the derivative of this. So the derivative of the first guy is a -2. The derivative of the second guy is just a 2. And remember, the only thing that changes for the absolute value is, and there's supposed to be the word if in all these. I glossed over that. When you take the derivative here, you do not get the equal to. And remember, that's because we have that cusp point on the absolute value. So it's just greater than and less than, okay? So that's the actual derivative. Now, if you go over here and you do f of 3 minus f of 0 equals f prime of c times 3 minus 0, and we try to solve for f prime of c, then we'll notice that if you plug in 3 into this function, notice 3 is going to be bigger than a half. So if we plug that in, that would be 3 minus 2 times 3, so that's 3 minus 6, so that's -3. And if we plug in 0, 0 is less than a half, so we're going to use the bottom equation. So I'm going back to my original function. So that'd be 1 plus 2 times 0, so that's going to be minus, and then the value would be 1. F prime of c times 3. So this is -4 equals f prime of c times 3. That would be -4/3 equals f prime of c. There is no way that this could be part of this function because this has no x's involved, essentially. This is just two values. And if you remember, when we graph, so like at x equals 1/2, this is the derivative function here. At 1/2, which is about right here, so that's 1, we're saying that from the greater than side, you're at -2 forever, and on the less than side, you're at positive 2 forever. So how is it possible that we could have a value of C that would equal to negative 4/3, which is negative 1 1/3? It's never going to happen. So there is no C that can equal to negative 4/3 for the derivative, because it's not our fixed negative 2 or 2 that we get for those absolute values. Now, why did this happen? Why did this fail? Why does it not contradict the mean value theorem? The reason it failed is that in this interval, we actually have a non-differentiable point. X is what we'd call not defined at x equals 1/2. So not only are we not differentiable there, we're not continuous on 0 to 3, and not differentiable everywhere on the open interval 0 to 3. So that's why it failed, and it doesn't contradict the mean value theorem because we didn't check for those conditions to begin with, so you shouldn't have even been using the mean value theorem in this specific problem. So, and the reason that is because of the closed interval we picked. Now, if we'd picked a closed interval from 1 to 3, we would have been fine because, from 1 to 3, it would have been continuous on that closed interval, and it would have been differentiable on that open interval. So it's all based on not just is the function got an issue, but is the closed interval that you're even looking at around that issue? Is the issue within that closed interval? Okay, so that's it for the 3.2.